Far beyond the beaches and marshes of Louisiana, beneath the murky waters of the Gulf of Mexico, the seafloor carries the weight of one of North America's greatest geological experiments. Layer after layer of mud, sand, clay, and organic debris has poured out of the Mississippi River for thousands of years, building a sprawling delta that appears stable from above but behaves very differently underneath. Recent scientific mapping has revealed something deeply unsettling hidden below the Gulf waters near Louisiana. Enormous sections of the seafloor are not fixed in place at all. They are slowly deforming, cracking, sagging, and in some areas collapsing in gigantic underwater landslides stretching for miles and kilometers across the continental slope. The discovery raises difficult questions about the long-term stability of the northern Gulf Coast and the hidden processes operating beneath one of the most economically important coastlines in the United States. How much of the seabed is already moving? How large could future collapses become? And how vulnerable is a coastline already losing land faster than almost anywhere else in North America? The evidence did not emerge from a single dramatic discovery. Instead, it appeared gradually through decades of sonar surveys, seismic imaging, sediment analysis, offshore drilling records, and geological mapping conducted across the Gulf seafloor. Scientists studying the offshore region near Louisiana began noticing scars cut into the seabed, enormous buried debris fields, tilted sediment layers, and crescent-shaped fractures resembling the signatures of massive underwater landslides. Some failures appeared ancient, buried beneath younger deposits. Others looked comparatively fresh, suggesting that movement beneath the Gulf floor remains active today. The Mississippi Delta itself explains much of the danger. Unlike rocky coastlines shaped by ancient tectonic uplift, southern Louisiana is constructed primarily from unconsolidated sediment. The Mississippi River drains approximately 1,200,000 square miles, or more than 3,100,000 square kilometers, across the interior of North America. For thousands of years, the river transported colossal amounts of sediment southward into the Gulf. Fine mud, clay, silt, and sand accumulated layer upon layer atop older deposits. Much of that material remains saturated with water, loosely packed, and mechanically weak. Under normal conditions, sediment settles slowly and compacts over time. But the Gulf margin offshore Louisiana accumulated material at extraordinary rates. In some areas, sediment piled up faster than natural compaction could stabilize it. The result is a massive wedge of unstable earth extending beneath the Gulf waters. Gravity constantly acts upon this overloaded sediment mass, especially along the continental slope where the seabed angles downward into deeper waters. Over time, entire sections can begin creeping seaward almost imperceptibly before eventually failing in enormous submarine slides. Modern multi-beam sonar systems have transformed scientists' understanding of this underwater terrain. Earlier generations of marine mapping provided only crude outlines of the seafloor. Today, high-resolution sonar reveals submerged scarps, fault-like fractures, collapsed sediment blocks, and giant slide channels with astonishing clarity. Some offshore collapse zones near Louisiana measure several miles wide and extend for tens of miles or kilometers along the Gulf slope. Buried beneath newer sediment layers lie evidence of even older failures, indicating that submarine landslides have occurred repeatedly throughout the region's geological history. One particularly troubling aspect is the immense volume of material involved. Some offshore slide complexes contain billions of cubic meters of displaced sediment. These are not small slumps comparable to coastal erosion events visible from shore. They are gigantic mass movements capable of reshaping entire sections of the continental margin. In some mapped regions, blocks of seabed several hundred feet thick and miles across appear to have detached and slid downslope before breaking apart into chaotic debris fields. The causes behind these failures are complex because several destabilizing processes operate simultaneously beneath coastal Louisiana and the adjacent Gulf floor. Subsidence is among the most important. Large parts of southern Louisiana are naturally sinking every year due to sediment compaction, tectonic adjustments, and the immense weight of accumulated deposits pressing downward. In certain areas, the land sinks faster than global sea levels are rising. That gradual downward motion affects both coastal marshes and offshore sediment layers. As subsidence progresses, stresses within buried sediment change. Water trapped within mud layers may become overpressurized. Weak zones can develop where pore fluids reduce friction between sediment grains. Once the strength of the material falls below the force exerted by gravity, portions of the slope may begin moving. Scientists studying seismic profiles offshore Louisiana have observed evidence of slow deformation occurring over long periods before sudden failures take place. The role of oil and gas extraction has added another layer of debate surrounding Gulf stability. Offshore Louisiana became one of the world's largest centers of petroleum production during the 20th century. Thousands of wells, pipelines, canals, and drilling platforms spread across coastal wetlands and offshore waters. Extraction of hydrocarbons alters underground pressures within deep geological formations. Some researchers argue that these pressure changes may contribute to subsidence and localized instability, while others believe natural geological processes remain the dominant factor. Regardless of the exact contribution, decades of industrial activity occurred atop terrain already prone to sinking and deformation. The connection between land loss and offshore instability is impossible to ignore. Since the 1930s, Louisiana has lost thousands of square miles of wetlands due to erosion, canal construction, saltwater intrusion, subsidence, and rising sea levels. Barrier islands protecting the coast continue shrinking. Marshes that once absorbed storm surge are disappearing. River levees built for flood control also reduce the natural replenishment of sediment across coastal wetlands, depriving marshes of the mud needed to maintain elevation. As coastal environments deteriorate, the offshore sediment system experiences additional changes in how material is distributed and deposited. Hurricanes add another powerful destabilizing force. The Gulf of Mexico regularly experiences some of the strongest tropical cyclones on Earth, and major storms can drastically reshape the seabed within hours. Hurricane Katrina in 2005 generated enormous underwater sediment transport across portions of the Gulf Shelf. Powerful storm waves churned the seabed while intense currents displaced massive quantities of mud and sand. In already unstable regions, such disturbance can trigger slope failures or worsen existing fractures. Underwater measurements taken after major storms often reveal altered seafloor topography, newly exposed sediment scars, and shifted deposits. Unlike earthquakes, which release energy in seconds, hurricanes repeatedly batter the continental shelf for many hours or even days. The continuous agitation can weaken slopes gradually until sections collapse. Scientists studying Gulf sediment cores discovered layers associated with ancient hurricane activity, suggesting that storms have influenced submarine landslide processes for centuries. Methane buried beneath the Gulf floor presents another concern. Parts of the northern Gulf contain methane hydrates and shallow gas pockets trapped within sediment layers. Methane hydrates form when gas molecules become locked within ice like crystalline structures under cold temperatures and high-pressure conditions. If pressure changes or temperatures rise, hydrates can destabilize, releasing gas into surrounding sediments. Expanding gas reduces sediment strength and may increase the likelihood of slope failure. Shallow gas pockets pose additional hazards because they create zones of overpressure beneath impermeable sediment layers. If that pressure suddenly escapes, sediment can fracture or collapse. Sonar surveys have identified pockmarks, gas seeps, and disturbed sediments across portions of the Gulf floor near Louisiana, indicating ongoing methane migration beneath the seabed. In some areas, gas escape appears linked to fault systems and buried slide complexes. The possibility of underwater landslides triggering tsunamis receives far less public attention than earthquake-generated waves, yet the mechanism is well established. When massive volumes of sediment collapse downslope underwater, they displace water above them. Depending on the size, speed, and depth of the failure, this displacement can generate tsunami waves capable of traveling considerable distances. Most Gulf submarine slides are believed to produce localized hazards rather than ocean-spanning disasters, but the risk remains real. Historical evidence suggests that submarine landslides in enclosed or semi-enclosed bodies of water can generate dangerous surges. Scientists continue studying whether large future Gulf slope failures could threaten offshore infrastructure, shipping lanes, or coastal communities. Although the Gulf of Mexico lacks the tectonic conditions associated with giant Pacific tsunamis, underwater sediment collapses do not require earthquakes to produce hazardous waves. The scale of offshore instability near Louisiana becomes even more striking when viewed through seismic imaging. Seismic surveys operate by sending sound waves into the seabed and measuring how they reflect from buried layers. These profiles reveal hidden geological structures extending thousands of feet beneath the ocean floor. Offshore Louisiana, seismic records show folded sediments, buried faults, detached slide blocks, and stacked landslide deposits accumulated over immense timescales. Some regions contain evidence of repeated slope failures occurring one atop another. Ancient landslide debris becomes buried beneath newer sediment, which later fails again. This pattern indicates that instability is not temporary, but deeply connected to the way the delta system naturally evolves. Sediment loading, fluid pressure, and gravitational spreading continually reshape the continental margin. The Mississippi Delta itself has never remained stationary. Over thousands of years, the river repeatedly changed course, abandoning old delta lobes while constructing new ones farther east or west. Each shift altered where sediment accumulated most rapidly. Abandoned delta regions subsided while newer lobes prograded outward into the Gulf. This constant reorganization created uneven loading patterns across the continental shelf and slope. Offshore instability reflects part of that broader geological cycle. Climate change introduces another dimension to the problem. Rising global sea levels increase pressure on already vulnerable wetlands and barrier islands. Stronger rainfall events across the Mississippi Basin can alter sediment delivery patterns. Warmer Gulf waters may influence hurricane intensity. While submarine landslides near Louisiana occurred long before modern industrialization, changing environmental conditions could affect the frequency or magnitude of future failures. Coastal restoration projects now underway across Louisiana aim to combat land loss by reintroducing river sediment into deteriorating marshes. Massive engineering plans propose sediment diversions capable of reconnecting parts of the Mississippi River with sinking wetlands. These efforts seek to rebuild land naturally over coming decades. Yet the broader offshore sediment system remains dynamic and unstable regardless of restoration efforts closer to shore. Infrastructure vulnerability is another major concern. The northern Gulf hosts extensive networks of pipelines, drilling platforms, communication cables, and shipping corridors. Offshore energy production supports a substantial portion of United States petroleum and natural gas activity. Seafloor movement threatens these systems because submarine landslides can rupture pipelines, damage wellheads, destabilize platforms, and sever underwater cables. Previous offshore slope failures in other parts of the world demonstrate the destructive potential. Underwater landslides off Norway in ancient times triggered massive tsunamis and disrupted wide areas of the continental shelf. Modern offshore engineering increasingly incorporates geological hazard mapping specifically because unstable seabeds pose enormous financial and environmental risks. Louisiana's offshore region presents a uniquely difficult environment because instability operates alongside intense industrial development. Companies planning pipelines or drilling infrastructure must evaluate slope stability carefully using seismic surveys, sonar mapping, and sediment analysis. Even slow seafloor movement can stress underwater structures over time. In regions where creep accelerates or sudden failures occur, damage can happen rapidly. The geology beneath the Gulf also contains extensive salt formations that influence seafloor stability. Thick layers of buried salt deposited millions of years ago slowly deform under pressure, creating domes, ridges, and faults within overlying sediments. Salt movement reshapes surrounding geology and contributes to uneven stress patterns beneath the seabed. Some submarine slide zones appear associated with areas where salt tectonics altered slope geometry or weakened sediment structures. Deep beneath the Gulf floor, pressure and temperature conditions continue changing as sediment accumulates. Water trapped within buried layers may become highly pressurized because overlying sediments prevent fluids from escaping easily. Overpressured zones reduce effective stress between grains, making sediments behave more like fluidized material under certain conditions. This process increases the potential for large-scale slope failure. Even relatively small triggers can destabilize slopes already near failure. Minor earthquakes, hurricane waves, rapid sediment loading, gas expansion, or human activity may all contribute under the right circumstances. Often, no single cause explains a collapse. Instead, instability builds gradually until the sediment reaches a critical threshold. The northern Gulf Coast has always existed in tension between construction and destruction. The Mississippi River builds land by depositing sediment, while subsidence, erosion, storms, and gravity remove it. Offshore Louisiana represents one of the clearest examples of how rapidly geological systems can evolve even without towering mountains or active plate boundaries. The landscape appears deceptively flat and calm from the surface, yet beneath the water lies continuous motion. Scientists increasingly rely on autonomous underwater vehicles and remotely operated systems to monitor these hidden environments. Advanced mapping technologies now reveal details once impossible to observe. High-resolution bathymetry exposes subtle fractures and slide scars across the seabed. Time-lapse monitoring allows researchers to detect areas undergoing active deformation. Sediment cores extracted from offshore deposits preserve records of ancient collapses, storms, and environmental shifts stretching back thousands of years. These discoveries continue reshaping scientific understanding of submarine landslide hazards worldwide. For decades, underwater slope failures received less attention than earthquakes or volcanic eruptions because they remained hidden beneath the ocean surface. Improved technology has revealed that continental margins around the world frequently experience massive sediment failures capable of altering coastlines, damaging infrastructure, and generating tsunamis. Near Louisiana, the combination of unstable deltaic mud, subsidence, hurricanes, methane, industrial activity, and rising seas creates conditions unlike almost anywhere else in North America. The Gulf seafloor is not a static foundation. It behaves more like a slowly shifting mass under enormous pressure. One reason these processes remained poorly understood for so long is the sheer difficulty of observing underwater geology. On land, landslides leave visible scars. Faults can be mapped directly. In the Gulf, thick sediment and dark water conceal movement beneath hundreds or thousands of feet of ocean. Only sophisticated acoustic imaging and drilling technology made detailed analysis possible. Even now, large portions of the offshore Gulf remain incompletely mapped at high resolution. Scientists continue identifying previously unknown slide complexes and deformation zones. Some buried landslides appear vastly larger than originally estimated. Others show evidence of multiple stages of collapse occurring over extended periods. The broader implications extend beyond Louisiana. Many river deltas worldwide face similar challenges involving subsidence, sediment instability, sea level rise, and human development. Regions such as the Nile Delta, Mekong Delta, and Ganges-Brahmaputra Delta also depend on delicate balances between sediment supply and coastal erosion. Louisiana's offshore instability provides a warning about how vulnerable delta systems can become when natural geological pressures combine with environmental change. At the same time, the Gulf's geological evolution remains entirely natural in many respects. Long before modern industry or climate concerns emerged, sediment from the Mississippi River continuously built outward into deep water where gravity inevitably pulled material downslope. Submarine landslides are part of the delta's long-term growth cycle. The difference today lies in the concentration of infrastructure, population, and environmental stress surrounding the region. For coastal Louisiana, the consequences of instability are already visible above water. Marshes disappear each year. Salt water penetrates inland. Barrier islands shrink. Communities face increasing flood exposure. Offshore, the geological foundation beneath the Gulf continues adjusting under immense sediment loads deposited over thousands of years. The phrase sliding seafloor may sound dramatic, yet the reality is often slower, broader, and more complex than a sudden collapse. Some areas creep gradually for years before failing. Others remain stable until powerful storms or shifting pressures trigger movement. The process resembles a vast overloaded slope constantly seeking equilibrium beneath layers of mud and water. Still, certain ancient submarine landslides near Louisiana were unquestionably catastrophic in scale. Sonar images revealed giant detached blocks, collapsed escarpments, and chaotic debris fields extending across enormous distances. These failures moved volumes of sediment large enough to bury entire urban areas if transported onto land. The geological evidence leaves no doubt that the Gulf margin is capable of major underwater collapses. Future monitoring efforts will likely focus increasingly on identifying active deformation zones before larger failures occur. Offshore sensors, repeated sonar mapping, and advanced computer models may improve understanding of how sediment strength changes over time. Researchers also continue studying the relationships between hurricanes, methane release, subsidence, and slope instability. The Gulf of Mexico often evokes images of oil platforms, fisheries, hurricanes, and coastal wetlands. Yet beneath those waters lies one of the continent's most dynamic geological frontiers. The Mississippi Delta did not create a stable platform extending safely into the sea. It built a massive accumulation of soft sediment balanced precariously along the continental margin. Evidence now shows that parts of this underwater landscape are slowly moving, cracking, and collapsing under their own weight. Ancient scars mapped across the Gulf floor reveal a long history of submarine landslides. Modern technology continues uncovering signs that instability persists today. Offshore Louisiana remains a region where geological forces, sediment loading, storms, gas pressure, and subsidence converge in ways that continuously reshape the seafloor. As coastal land loss accelerates and environmental pressures intensify, understanding these hidden processes becomes increasingly important. The Gulf floor near Louisiana is not simply resting beneath the water. It is evolving in real time, carrying the weight of centuries of sediment while gravity steadily pulls portions of it seaward into deeper waters.